I hope you can see my screen. So
We can.
I would like to give you a short comic version, and it's really a comic about how a job scheduler or batch system works. So you see here an animated GIF, and what I like to show you is a PowerPoint of that. So I hope you can see my PowerPoint. So here I have a small comic cluster. The cluster has 4 nodes from 1 to 4, and each has 8 cores, which are labeled from 0 to 7. So this is a small cluster. On a typical cluster, we have hundreds of nodes, and these days the core count is 128, 256. So it's a lot. The numbers are a lot larger, but the principles stay. And for explanation, I like a small example. So let's see, we have an empty cluster. And then the first user connects, and he wants to run a serial job for 8 hours. So there's job number 1, which asks for 1 core, a serial job, and it runs for 8 hours. So the cluster takes the job and picks a node. So in this case, it has taken node number 1 and placed it on core number 0. So the time grows up like this. So we are currently about here, and it just runs that job more or less directly. So the second user comes in. He wants 1 full node of 8 cores and wants to run 4 hours. So the cluster picks a node. In this case, it has picked node number 3. And the job can start running. So time-wise, that much time has elapsed until the second user came, and the job starts running here. Next user comes in. He wants 2 nodes with a total of 16 cores. 2 nodes are 8 cores each, and that should run for 8 hours. So the system has a good look at its nodes and discovers if I give node 2 and node number 4 to job number 3, I can run that directly. So this job gets 8 cores on that node and 8 cores on that node. We don't have any nodes which have 16 cores, so that is the best it can do. And then it is up to the job how the data passes up to the user and his job and his software, how the data passes from node number 2 to node number 4. Okay, now it gets interesting. Next user comes in. He wants 3 nodes, a total of 24 cores for 3 hours. Time-wise, we are about here, but we do not have 24 cores idle. So what can the system do? It can schedule the job to run in the future. So when job number 3 has finished, then it could give the nodes number 2, 3, and 4 for job number 4. So the job number 4 has to wait in the queue until job number 3 is finished. So that's the plan. Another user comes in. He wants 1 node of 8 cores for a long time of 12 hours. So time-wise, we are about here. And in principle, at that point in time, there would be 8 cores idle, so we could start running the job. But the problem is that job number 5 wants a long time of 12 hours, and there's not enough. So what can the system do? It has decided, no, we are not putting job 4 to a different time. It has discovered, if I just wait until job number 1 has finished, then I can start job number 5 on that node number 1. So it's also scheduled for some time in the future. That is here indicated with the blue color. So now another interesting thing happened. If you just look at that, another user comes in, and he wants 2 nodes, 16 cores for 4 hours, and that job has a very high priority. So perhaps because the user hasn't run so much and he still has a lot of allocation, but the users for job number 4 and job number 5 have already used up the allocation, so then the job number 6 gets preferential treatment. So if you have a look, what happens is that the system discovers running jobs like 1, 2, and 3 do not get terminated, but the earliest I can run that job is if I give it that node and that node from that point in time, and then it has just rejigged the job number 5 and the job number 4. So in principle, job number 4 got in earlier than job number 5, but by running job number 5 here, job number 4 doesn't get any delay, so that is what happens, or what the planning now is. So once job 1 has finished, job 6 gets started. Once job 3 has finished, job 5 gets started here. And once job 6 is started here, job number 4 goes in. So what we see here is that although job number 4 was started earlier, because it needs so many cores, 24 cores, 3/4 of the machine, job number 6, because of its high priority, and job number 5, because it can be fit earlier without impeding on job number 4, gets started earlier. Then the job number 7 comes in. It just asks for 1 core. Time-wise, we are about here. Here, plenty of cores idle, but because of the 6 hours job time, it can only be put at the end, and that is what the scheduler does. The job is planned to be run a long time into the future. And then the job number 8 comes. It asks for 4 cores, so quite a bit of resource, but it's only 2 hours long. And since we're time-wise here, it can just fill in at that point. So what is the offshot? Here are a few things. So the first one is that the job queue is a job queue. It's like a waiting queue at the cashier's desk. Then on a parallel machine, there's a lot of assessment. If you need a lot of resources, typically that cannot be run directly. If you need a small amount of resources, the jobs can often start it earlier than its point in queue without impeding on anyone. So here you see a description of what I explained to you. So the key points, the submitted jobs are waiting queue. The jobs start executing once it's their turn. And the anticipated start time can move forward or backward depending on other users' action. So one thing to comment here is that the times I have given here are the times the user specified. We will get that in a minute. But typically jobs finish earlier than they are specified. That is highly recommended best practice that you are a bit generous with specifying your job time. We will discuss that later. So because of that, because of most jobs finishing early, the start time of a job might move forward in time. On the other hand, we have seen if something else comes in, which is higher priority or stuff gets rejigged on some other optimization principle, your job can also move into the past. So this anticipated start time is an estimate, and that can change. And for that, in order to get in the queue, you have to describe your computational work to the system, and that is done by a script. And that is what the rest of the course is about, how to write these scripts, how to submit these scripts, and how to interact with the system when it is processing your script. So important, computational work needs to be submitted using the job scheduler, and you need to describe your work at the time of job submission, since you might not be there, for instance, because it's out of hours once your job starts. Here are a few comments on priorities. The priority is affected by many factors. These may include how long this job has already waited in the queue. Typically, they accumulate points, and the more points, the sooner they run. And how many resources, for instance, CPU hour, the project has used in relation to the allocated resources. So typically at NAISS, we have a policy. If there's time left, you have spent your allocations, but other users don't want to spend their allocation, then we run your job instead of letting the time go to smoke. So these jobs get added to the end of the queue with the low priority when the allocation is spent. And then those which still have allocation left, they will overtake it until, yeah. Okay. And system administrator may adjust the batch system rules to ensure all user groups can run in line with the resources allocated to the project. I've seen that quite often. Sometimes users find out something that submit jobs in a way that they get way more jobs through the queue than they should. And then the sys administrators often start adjusting the parameters of the scheduling system such that everything is fair. Okay, that was the